Okay, so I want to show you a little bit about Pharo. And the first question is, what is it? And actually, it's a programming language, but at the same time, it's not only the language itself, so how you write it as text and how it's compiled, but it's actually a complete environment in the sense of a development environment. So when we will see a demo later, when you open it up, it opens its own window, and inside there is the whole Pharo world containing the simple language, which is a Smalltalk-based language, and a whole development environment, libraries, and everything. It's object-oriented, standard how we know it. It's very dynamic, so once it has no type system, so it's dynamically typed, and it's very dynamic in the sense that it is reflective. So it has a model of itself, embedded in itself, that you change by executing code. This means that when you program, you actually explore and change a running system instead of programming that text that you compile and then run. So in the end, it is, in a way, our goal to build the ultimate programming environment out of this. And in some way, it already has some effects of that. Pharo is MIT licensed, so that means you can use it even in commercial projects. So even if you make a company and you use it, you change it privately, that's okay. So you don't need to give back the code that you change, which is very important for commercial projects, because if you use GPL, it can get really complicated, especially in a language that is so where you don't have a clear notion of linking to external libraries and things like that. It runs mostly on Mac, Linux, and Windows. We do have versions on Android and iOS, which are pure interpreter versions, because doing a JIT compiler on these systems is either not allowed or very difficult for Android. One interesting aspect is the community. So we have around 500 people on the mailing list, maybe in the meantime 600, that are there to answer questions and that all every day help and build and commit fixes and things like that. And it's improving steadily, and steadily means literally every day. So every day we have a tiny, tiny thing that we improve in the system. And this reaches really from tiny improvements in the sense of refactorings that just make code easier to use or deletes something that sounds a bit strange. Is that good? Yeah, from small things, removing that code to big new subsystems and things like that. So what I will, first. So we started actually in 2008. So the first version was released in 2009 after 1 year development. And 2.0 is the current stable release. There were a lot of intermediate releases, so 1.1, 1.2, 1.3, 1.4. So that in the end we had around 1 release per year. And this is something that we now, starting with 2.0, do more in a defined way. We want to do 1 new release every year. So the idea is that we release around March every year, 1 stable release, and we continue to build an unstable development branch that then 1 year later gets released again. And the idea is that all the people that use Pharo, either for research or for commercial development, are supposed to use the stable version, where all the external projects then get ported to, the libraries. Whereas the development itself will happen always on the unstable branch for 1 year, where then some of the external libraries will not work because people have not yet come around to port them. And one of the very important aspects is that when we started, we clearly said we will not necessarily be 100% backward compatible between the releases, because this is the idea is to really build something new over the long time. And if you're always 100% backward compatible, that's really difficult. And we have, over the last years already, been able to clean up some major things with this strategy. So that you are able to follow a bit when I do demos, I want to do a short introduction to the language. I hope that should take around 10 minutes. And it covers more or less the complete basic language of the system. So Pharo started with the code base of the original Smalltalk 80 in the form of Squeak. So it's really literally that there are classes in that system that date from 1978. around. Even so, some of them were removed in the meantime. For example, the compiler was literally from back then, and up to a point that it was actually implemented completely wrongly. So for example, parser was a subclass of scanner, but this is a use relationship and not an inheritance relationship. But people didn't know back then, so because they just invented all these things, they did really bad mistakes. And these things are now slowly being fixed. So we are replacing a lot of the old code. But there is still code left from that old times. And especially the language itself, so the basic language that you write, is still very much Smalltalk. The goal is to develop it further, but as Smalltalk is an extremely flexible language, it does not mean that the language itself will change too much. It's more that the libraries and the language that is implemented in itself to a huge extent will be different. And there are already a lot of examples of that, especially in the reflective capabilities that we have in the system. They are already much advanced compared to Smalltalk 80 or Squeak. The language itself is extremely simple. So one interesting way of thinking about it is of what it does not have compared to all the other object-oriented languages. So there is no syntax for constructors, there is no type declaration, no interfaces, no private protected scoping of methods, no type system, no parameterized types, no nothing of that. So it's really, if you take away a lot of some things from any object-oriented language you end up having this. So it's kind of like the essence of an object-oriented class-based language. And the interesting thing is that it still stays extremely powerful, even without all these features. So if I want to give a quick introduction into this language, then the easiest thing is to just tell you a little bit of things, because it fits really nicely in what you know already about all these object-oriented languages. So one thing is that objects are instances of classes. That's clear, object-oriented language. So for example, if we have, in this case, a point object, we can ask it for its class, and it will tell us that it's actually a point. And if we do this in the system itself, we can actually, so if we start up Pharo, then it looks like this, and we should first do a bit of bigger fonts, like this. So if we are in Pharo, we can directly enter code and execute it. So for example, if we want to have a point, we just say 5 at 4, and this is a point. We can execute it, it tells me, okay, prints out the value back, and then we can ask it, which class are you? And it tells me I'm a point. Very nice. Then one thing that is interesting is that classes are objects too. So as opposed to other languages where you have their text, in this language, a class is an object directly. So if we go back to our demo, we can, for example, say, so point as a class is an object. Directly in the system, I can print it, and it prints back its name. And I can now ask, for example, for selectors. This is all the methods that the names of the methods that it implements. And it can print them out, or can ask for the size of them, and it tells me, oh, I know 100 methods. Interesting. Or I could ask for the methods themselves, the objects that are the methods. So methods. And then it prints out, I mean, it should be the same, 100. But this one is now a method object. So for example, the first one is point x. So the method that implements point x. And they can even ask it for its source code, for example. And then it prints out, this is my code. So it's really an object, in a normal object like your objects that you create. And this goes extremely deep into the system. So everything is an object. So this we did. So an object-oriented language with classes. Methods are public, always. You cannot change it. Instance variables are always protected. So you cannot get to them. There is no syntax to get to an instance variable other than implement an accessor, and then it's public. Very simplistic, but it's amazingly powerful. Single inheritance. We did add actually something called traits already back in Squeak 3.9, so this Squeak version that became Pharo 0 in the end. We added something called traits, which is groups of methods that you can put into classes. So classes are composed from traits, so that you have the features of multiple inheritance if you need them. And this is an example of an object of a class in the system that kind of shows a bit this single inheritance thing. So we create classes not by having some special syntax for it, but by sending messages to existing classes. So object is the class, which is an object itself, and it understands a very long method with lots of parameters. We will see a bit how to, so it's the same syntax like in Objective-C. So you have the parameters are interspersed in between the names of the method. We will see later a bit in detail how this looks like. And so this means here this is object, we make a subclass point, and it has two instance variables x and y. And this is literally how it's defined in the system. We'll see that later. This slide should have come maybe before to explain that. So we have three kinds of messages that we can send to objects. We have seen already this one, which is a message without a parameter, like we saw for selectors or methods to class, and here we send it to integer. We have binary messages, which is for mathematical expressions, where you have 3 plus 4, so this is 3 is the receiver object, and it's an object, so even an integer is an object. We have a plus as the name that we send for the message, and we have the parameter 4. This is for typical, so there was a predefined set of mathematical expressions that you can, of names of mathematical expressions that you can use here, around maybe 20 or 30. And then there are the normal messages with parameters, which use these keyword messages. So the method that we call is raised to modulo, and we put the first parameter here and the second one here. This is used nowadays in Objective-C, and since then got quite prominent. So in the early days, I think this was one of the biggest problems of the language, that people really couldn't get used to this way of doing things. I need to put this down, I think. Okay. So, messages. One important object that we have, and I think I will demo that directly, is because with this language until now there is not a lot. I mean, we have methods, we can send messages, we have objects, but how can you do things like control structures? And this is actually implemented in this language using anonymous functions that have a very concise way of writing them down. And I think the easiest thing is I show you that in the live system. So if you want to define an anonymous function, you just put them in square brackets. So for example, we can say 1 plus 3. And if we evaluate that, then this is an object. And this object is a function that is not yet evaluated. So that means we can assign it to a variable, for example. So to b, let's do that. And now b is this block object. And we can now evaluate it by calling a method on it, by sending a message, value. So if we say value, then at that point we evaluate this code block and we get back 4. And we can put a parameter into it by using this syntax, a plus 3, and then we can say value 5, and we get 8. And this, the interesting thing is that this is a language construct. It's an anonymous function, but at the same time it's an object. So I can ask it, what class are you? Oh, I'm a block closure. How much methods do you have? Block closure. 110. Oh, that's interesting. So it's really an object like any else in the system that you can use for doing things. And what we do with this is control structures. So in this language, every control structure is actually implemented using message sends and blocks. So for example, we don't have any special syntax for doing something n times, and instead we implemented on integer, here, a times repeat method, which takes a block as an argument. And this method actually executes this block 4 times. Deep in the system, of course, the compiler detects that this is a control structure and optimizes it a bit so that it's actually fast. But conceptually, it's just a message sent and a block. And yeah, with this, everything's implemented. For example, on number, we have max, and this just returns the maximum of 2 numbers, and this is implemented using if. And so we say, if self is smaller than a number, if true, we execute this block. If false, we execute that block. So, and if true, if false is again a normal method in the system. And we can even browse them. So that's kind of, so look at them in the system. So for example, you can check if true, if false, has an implementer. There's a nice shortcut where you can use the menu here called implementers, extended search, implementers. Then it shows all implementations of if true, if false. And Boolean, of course, says, yeah, I don't know, my subclasses do it. And false, it's just implemented as false alternative block value. And in true, it's implemented as true alternative block value. Of course, deep down in the system, it optimizes this because else it would be very, very slow. But conceptually, this is the thing. And we can even ask the system, who uses if true, if false? And then it tells me there are 3,822 places in the system where if true, if false is used. Or just if true, who sends if true? I need to make it a bit bigger because of the font. 6,650 places have an if true. Kind of nice. Times repeat, we could look at times repeat, implemented on integer, so that it works for both small integers and large integers, which are only bound by memory size. And here you see that it's implemented relatively simplistic using while true. So we have a count, as long as the count is smaller than the number itself, while true. We execute the block, and then we set the count up once. Good. And this, in the end, is the language. So the only additional thing that we have seen already when we looked at the methods that were implemented is that there is a syntax when we define a method. So that means we put the name of the method at the beginning, we put the parameter after, and then often a comment here, and then we implement the body of the method using the syntax that we have seen. So we have a return, variable access, and then lots of message sends that implement everything. So even end, in this case, the message send, getting a block, very, very simplistic. And this is everything. So someone once did a puzzle and said, I want to write a small method that contains every syntactical element of the language. And this is it. So there is nothing else than this. So this is all syntax that we have. So all different kinds, so even containing all kinds of objects that you can write directly, like character, symbol, which is used for the names of methods, string, integer, float. Yeah. Complete syntax of the language. And this, of course, means it's extremely flexible. So you can do a lot of things with this syntax, even so you don't change it. So you don't need to change the syntax to introduce something. So if at some point we want to introduce promises or futures or whatever for parallel programming, then we don't need to change the syntax at all, because this is so little that we can actually just do whatever we want. And another thing that is clear is that a language that is that simple without an environment is completely useless. So some people always say to us, yeah, I would like to play with your language, but if it does not run in Emacs, I don't care. But a language that is so tiny like this in Emacs, it makes no sense. There is just not enough language that you could do anything with it. You need a dedicated environment. And this environment is extremely closely linked with the language, which is why it is so powerful, but of course it's a bit dangerous too, because there is no clear separation between the language and the environment, and often when people build complicated, even commercial projects, they start to change the language slightly. And that can, of course, be problematic or powerful, depending. And so for the tools, the basis is reflection. So everything in the system is implemented in itself, and that means that the tools don't need to re-implement all these things, but they just use the reflective layer of the system. So the browser, code browser that you saw, when you compile a method, it does not implement this like, oh, I need to call the compiler, and then I get a method, then I take the method and put it into a dictionary of the class or something like. No, what it does, it just tells the class, someone gave me a piece of code that he thinks that should be a method. Can you do that? And then the class makes a new method, and that's it. And so reflection is the basis of all the tools. In some cases, of course, the reality is a little bit less nice than it should be, but it's quite far already. So classes, methods, packages are objects, very nice. And all the tools manipulate these objects. An example that we have seen already a lot is the class browser, which just manipulates classes. So it has, with the big font it's a bit messed up, but nevertheless usable. So it has here the packages, then the classes with the subclass relationship as a tree. So you see our method context, the subclass of context part, for example. Compiled method is the method of something. But we can look anywhere. For example, you can even look at things like assembly instructions if you wanted to. Do we have an example of this? Let's see. I think this is SMG tests. Yeah, so here you can, for example, see how we write assembly code using this extremely flexible syntax. I mean, this is assembly code for x86, but it's written in Smalltalk syntax, calling on some kind of builder object to do the assembly code. And this is used in the system, for example, for doing assembly FFI, so C code callouts. So kind of nice. So for example, to see some, if we want to see a demo. So this one is a demo that shows how we can use Cairo vector graphics from within the system, and this uses the callouts to C using the our own x86 assembly system. Kind of nice. And yeah, this is the browser where you can look at everything. And it's one thing that when you start, you always ask, do you have documentation for the libraries and things? And what you learn after a while is that the browser shows you everything. You can just look at all the code, and you stop reading documentation, you start reading code a lot, which is very nice. Another thing that is interesting to see is the so-called inspector. So if you have an object and you want to actually look at it, then you can use the inspector, which is here. So this looks into a point, and it tells us the class so that we don't need to look it up. And then it shows us all the instance variables, and we can look at all those instance variables, and we can even change it if we wanted to. So this looks into objects. And one nice demo that I like to do always is that there is an object which is the whole graphical user interface that you see now. Let's make another window open. And if we get an inspector for this, then so one thing is you can get a tree inspector that shows you these things as a tree. So you can select the different kind of inspectors in the menu. It's slow right now. And then you can actually get a view that shows actually the object, which is a graphical one, inside the inspector as a graphical object, which is useful when you debug graphical stuff. But if you look at the system itself, it looks like this, and which is very funny if you think about it. So, and it's live. So if I move this, then it should update again. So kind of nice. A bit slow, but nice. And so this shows that everything is actually implemented in terms of objects. Even things like, so if you go, so there is something where the hand here is actually the mouse cursor. So, and it should be possible. Yeah, so now we have an inspector just on the hand, on the mouse. And we should see, yeah, that the mouse, when you move it around, that it actually changes the coordinates. Updates not directly, but after a while. So that means that everything is implemented in this system, down to things like the damage recorder. I think this is even in the world state here. Yeah. So if you want to look not at this one here, this is the class that is not interesting. So even the thing that does the repainting of this and records the invalid rectangles, you can quickly see how it knows about some invalid rectangles, and then after it repaired them, it deletes them from its list. So that means that the whole system is implemented in itself. Graphics, yeah, kind of nice. Another thing which I can quickly show is that actually how you make a new thing. So if you want to make a new class, then what you would do is you would first make a new package, demo, which is empty, and it directly fills out here a piece of code that you can use to make a new class. So if you want to make a demo class, we just write demo here, we accept, and boom, we have a demo class, and we directly can say demo new, and it works. And if we add an instance variable, so we can, and what is really funny, if you say a is assigned to demo new, then we can print look at A, and it's now an empty object. Why is the inspector so slow? Something is wrong. So it has no instance variables, but if I now add an instance variable here, recompile, and look at the same object again, I mean the same object, not newly instantiated, then we suddenly have an A variable. And that this is actually the same object, we can easily prove. So we put 4 into A, we close, we add a B, accept, and if we inspect A again, then we should get 4 in the A that we put in and a new B. So that means we can, when we change the class, all objects of that class are updated on the fly. And that's very powerful, because that means that you can actually very much, when you develop, explore the system as you develop. So it's really interesting that at the beginning you think, oh yeah, that can be handy when I debug or something like that. But over time you start to really change the way you develop completely. So you stop thinking about what might happen, but you always look at what happens. So you always change something, try out, look into the object, see that it works or not, and change it again. And up to the point that when you then go back to another system, you start to feel really, really constrained. Because there are no compile time here, no compile. So it's not that when we edit something that we need to compile, restart. Not at all. We can even keep our objects live, and they will change with the code a little bit, to some extent. I mean, when we add instance variables, we get the instance variable in the objects and things like that. So very nice, and it's really, after a while, a completely different way of working. So inspector we have seen, changing classes at runtime. The question is, how much time do we have? I guess a bit more. So one other thing that I always really like is things like when you want to know about your system, how big are you? So for example, what we can do here is we can always say things like all classes. So we have a global namespace, and we can ask, okay, how big are you? Okay, we have 3,781 classes, but it includes the tests. We can, when we could iterate over our classes to get the methods, but we could do something else. We could say compiled method all instances size, and it gives us all current instances of compiled method in the system, which is 71,307. Or we could calculate how much code some parts of the system have. So for example, if you want to know, let's take point that we played with, point lines of code, 528. And lines of code is implemented on compiled method like this. So it has a lines variable, it gets the source code, and then it calls line indices do, which is implemented on string, to count all those lines that are not empty, because empty lines do not mean anything. But it counts lines with just a bracket on it and all comments and all the things. And this one could, for example, with a bit of magic in a one-liner, calculate this amount of source code in the system. Inject into. So we iterate over the whole all classes, each plus, and keep a. So we use a method that is predefined on all collections, inject into, which kind of folds together using a running tally. Sum plus each lines of code. This is not completely correct because there are the traits that are not classes, and there are class-side methods that I think the lines of code do not take into account. But more or less, this should work. So as the source code is not in the memory but on disk, and the mechanism is a bit old and slow, this takes a while. And it, of course, goes line by line over everything. But so we see that this has 414,000 lines of code right now. But this includes comments, tests, and it includes even all the data of, so because we have right now no way of really storing files into our system, it even, if you have, for example, an icon, it's saved as a string, and this is counted in it too. So it's maybe not as large as it looks like. So that's quite nice. Okay, yeah, there's much more, and I cannot even come close to show anything. So if you are interested, there are now 2 books. So we have the first one, Pharo by Example, which is sadly for Pharo 1.0 and very much out of date. But we will do a new version for Pharo 3, which should be available early next year. And there is a second book, Deep into Pharo, about the more about external projects that are interesting and about more core concepts that are not for beginners, but for people that want to change the system itself. And that was released in September and is up to date. And has some quite interesting things. Yeah, and then, so it's actually used in industry, not only in research. So for example, a company in Cologne uses this system for an API monitor system, where so a customer of theirs came and said, and had problems with stability of external APIs, and the question was always, is the API down or is the iPhone application not working? And so this was the resulting application that was built that continuously monitors an API, a SOAP API, and makes nice statistics. So, and you always know, is my application wrong or is the API down? So a monitoring service for backend interfaces. And this is implemented completely in Pharo. And another thing that was implemented in Belgium is the T3 navigation system, which is a track and trace product for logistics, which is part of a bigger product. So T3 is a huge solution for these in this space, and they made a small entrance product which is implemented as a web service in JavaScript, HTML5 Ajax as on the client, and then a backend in Pharo completely. And this company actually contributed all the HTTP library, the current one, to Pharo. And it's really amazing, the libraries that they built. And this kind of collaboration between open source, research, and industry is something that is really interesting. And so we are trying to foster that a bit. And what we did over the last years is to work with INRIA to set up a consortium for Pharo, which is meant for actually companies like that, institutions. So there's the concept of a research membership, and, for example, user groups, if we ever have local ones. And the idea there is that they have a way of communicating directly to the core team and to kind of set priorities of what needs to be done and to provide resources of doing things. And we are in the meantime at around 12 members, I think. Most of them are small companies. One is Beta9 that did the track and trace product and contributed the libraries. But we have even some bigger members like VMware and INRIA itself. Yeah, so this is the more commercial direction, and then there is the research direction. So we are using Pharo to do research, but it's a bit detached. So we use Pharo as a research vehicle, and we do experiments. And some of these experiments are clear they are research experiments to learn and not something that we want to ever have in Pharo at all. Or where it's clear that if we would add it, it would be so much work that it would be impossible, or maybe it's a long-term thing or something like that. But on the other hand, we really want to feed back the research results into Pharo itself. So the idea is to not just publish papers and then, okay, paper finished, we throw everything away, but instead to really rethink what of these results on the research side can we put back into the system so that it gets stable, and that then the next PhD student can actually start with a stabilized ground that includes the work of the PhD student before. Maybe in a completely new, re-implemented way, but the results of the research should be reusable. And that is actually working already quite well. So we have already in Pharo 3 lots of results back ported from research, which will enable further research in a very nice way. And we are currently working on a lot of things. So one is that I explained in the lecture yesterday is, for example, that we want to improve reflection quite a lot. So we have already in Pharo 3 the basis for better instance variables, where instance variables are real objects and where you can make subclasses of this class and make your own instance variables that are special. For example, active instance variables that always, when you store something into them, do something special, or typed instance variables that only can hold one certain class, objects of a certain class, things like that. There's work on getting a really good, very modular proxy model directly into the language so that you can actually put a proxy on any kind of object and it will work everywhere, even in the cases where things are optimized down in the deepness of the system, which is very interesting for things like distribution and maybe even concurrency in the future. Or there's work going on structuring the reflective API better, so that, because reflection is very powerful, but on the other hand, it's extremely dangerous. If you use reflection in your end-user program without thinking, it can actually be very destructive. Another idea in that direction is to ask the question, can't we, with all these objects in our system everywhere, can't we actually move the source code into objects? I mean, instead of having this text, can't we use a object-oriented representation of code? And we already in Pharo 3, we have an AST behind. In every tool, there's an AST behind. And things like navigation and context menu is using that information. And the refactoring tools is using the AST already. And the question is, can't we go further? Can't we actually, maybe we don't need to even store text. Who knows? Maybe we can have an editor that directly transforms AST with every keystroke, something like that. And we want to use that for behavioral reflection so that we can actually deeply change the behavior of a computation, for example, when we want to do profiling or other things, or maybe going into directions like aspect-oriented programming, things like that. And another interesting project that we are kind of attacking from multiple perspectives is the question, can't we put this concept of, so now we have this, so all our Smalltalk objects are in the memory, and and the normal way is that you save that into a file, and when you start up, this file is put back into memory, and everything is the same that it used to be. It's a bit like what we know now from visualization, that you have image snapshots. And one idea that we had is to actually make this concept of an image something that is a first-class concept in the language, so that you can actually say, inside Pharo, you can actually say image new, and then you get a language image, which is empty, and that you then can fill, that is one object to the outside, so you cannot reference inside. It's really a unpenetratable object, and that you then can fill up with whatever you want, with maybe a Smalltalk kernel, a small one, and then you would have a very small Smalltalk system that you can use for whatever you want. And as it does not reference to the outside at all, it could even maybe run in parallel to the rest. Or you could use old, so if you have a library that you really need to use, and it's really for an old version of Pharo, you could actually maybe just run that library really encapsulated in an old version of Pharo inside Pharo itself. So we are exploring these things, and there is a lot of work to be done, but I think that this will be very interesting in the future. And I'm coming to the end slowly. So one interesting thing that we are doing all the time is so-called sprints for Pharo. And the idea here is that we meet somewhere where there is a group that is using it for research or commercially, and we organize a day or an afternoon where we sit together and actually do pair programming on the system itself. And the idea here is to do the boring stuff. I mean, to look at the bug tracker and say, yeah, nobody looked at this for 3 months because everyone knows it's really painful, so maybe we do it now with 2 people over a day or something like that. And this is very successful. We did a lot of them. I even didn't list all of them. The next one will be in Buenos Aires next week, I think. And we plan to do that regularly in all the places where it's used. So in Lille, of course, we have it every 2 months maybe, and but there are other places that do it often too. Yeah, this is it. So if you are interested, feel free to download it and play with it, or to even join and help building the system. It's a lot of fun, I think. Thank you. If you have questions. Yeah, so
That it has to have some persistency, has to have maybe some transactional capability.
yes. So what we do right now for big things is that we interface with databases. So there is, for one, a library for kind of typical old-style databases, like Oracle and things like that, which is more used in commercial settings where this is in the requirements. What is used lately a lot is NoSQL databases, where there is some quite good support in Pharo directly. For example, CouchDB, I think, is one of these things that is used a lot. And then there is actually another system that is very interesting for this, which is a database, an object-oriented database called Gemstone, which is from the old times, from the 80s. They started in the 80s, but it's continuously developed. A commercial project, which is an object-oriented database, one of the last that survived, which actually contains internally a complete Smalltalk system. And they are selling it mostly as an object-oriented database to customers, but you can use it like a Smalltalk system. So what some people are doing that do really big style data stuff is that they use Pharo in combination with Gemstone. So they keep their data in Gemstone and do maybe other things in Pharo, or even sometimes deploy completely in Gemstone because it's a complete Smalltalk system, and develop in Pharo. So they use Pharo, the browser, and the tools, and they have a version of their system, a small one, running in Pharo to debug and to develop. And then when they deploy in the big style, in really big terabyte style of, or potentially terabyte size, then they go completely Gemstone, which is a very amazing system, and it's hard to compete because it's fully persistent. The image can be terabytes size, and it can have multiple VMs on this, and it's very nice. And else, of course, for smaller things, what people do is they just sometimes use Pharo itself. So if you have a couple of 100 megabytes, there is no need to do a lot.
And you have to serialize.
Right. So we have an object serialization framework in the system, which is very powerful for that. Or you can, which is mostly not really good for long-term deployment. You can save the image, the snapshot. But that's not really good right now, because the danger there is that if something goes wrong and you save a wrong image, then it's a problem. So what people did in the past is that they used the object serialization, for example, for persisting data. But it's clear that there is something where we need to explore more in the future. Especially good support for databases is very important. And maybe getting some of the ideas into the system itself.
How about scientific computing? Algebra solvers or number crunching?
There is some code about numerical methods that is relatively old, but I don't know too much about that people do it. It is actually potentially not a bad system. For example, the integer, that it automatically flows over into a large integer and things like that. But people are not using it for that too much, I think, right now.
Can you run Pharo without the graphic? Can you run Pharo without the graphic?
Pharo without graphical user interface, yes. So we did actually, we did actually quite a lot of work on that over the last years, because at the beginning, Smalltalk traditionally and Pharo at the beginning was purely this graphical system. But what we added is that you can now run everything headless from the command line and very easily, for example, start processes, and it actually prints out error messages on the error console and all these things. So it actually works quite well now headless compared to the old versions. But of course, what is always, or what is not yet good, is you cannot, if you want with some normal editor like VI develop source code, it's a bit hard. But on the other hand, the language really is not nice for that. So the power of it comes from an integrated environment. But what you can do is that you can develop, and then when you are finished and you deploy on the server, you can do it completely headless. That now works very, very well. Yeah, there was a lot of work being done, especially in Pharo 2 and Pharo 3, so that you get, for example, when an error happens, that it prints out on the error console, and it even has nice color highlighting of the error and all these things. And quite nice. Yeah. Okay. Thank you.
Thank you.